All right, good afternoon. So I did update the slides on Moodle. So they're just better than what they were. So if you happen to have printed the slides out or whatever, you may want to end up looking at the new slides. Okay, so last time we left off, we talked about density. We talked about prefixes, significant figures, and how to do significant figures in calculations. So let's just, let's do a significant figure calculation problem. And we'll specifically do it for density so that we get all that practice in at once. Okay, so. Space does 22.04 kilograms of a met space goes 22.4 kilograms of 3.4 grams. All right, how much space does 22.01 kilograms of a metal with a density of 3.4 grams per milliliter take up? So I want you to solve that. And then I also want you to use the correct number of sig figs and make sure you're giving correct units, hint, hint, wink, wink on this problem, okay? Okay, so with this problem here, it's a density problem. So we can write out if we want density equals mass over volume. My given information, I know the density, which is equal to 3.4 grams per milliliter. I also know the mass. The mass is equal to 22.01 kilograms. It says how much space. So we're trying to find the volume. Now, one thing to note about this is if you look at the density, it's in grams per milliliter. This is in kilograms. Those units have to match up with each other, otherwise we can't plug them into the equation. So we need to get out of kilograms and get this thing into grams. So as you're running through these calculations, always making sure that your units are the same, otherwise the equation doesn't plug and chug correctly. So in order to go from kilograms to grams, King Henry died before 3 hops, 1, 2, 3. So it would end up being 22010 grams. Okay. Now I can plug it into my equation of density equals mass over volume. I'm going to isolate for volume. So V will end up equaling mass over density. These two guys will split places. Right, so they'll flip-flop. So now I can figure volume is equal to this 22010 grams divided by 3.4 grams per milliliter. This is a place, this is a useful time to see why we want to add our units when we're running calculations. So I can see there's a gram here and there's a gram here. I know those guys are going to cancel each other. If I had plugged this in, the 22.01 kilograms, the kilogram would have been here. That would have been an indicator for me that something isn't working out because the units aren't canceling. So 220. All right, so I got 647.3.529, yada, yada, yada. Units on this are going to be milliliters. Here's the only remaining unit under a fraction bar. Under a fraction bar, actually, we'll put that back to the top. Now, this thing here has 4 sig figs. This thing here has 2 sig figs. So I really only get to honor 2 significant figures. So I get to keep the 6 and I get to keep the 4. The 7 tells the 4 to round up. So we go with 6, 5. I have to fill in zeros for the remaining spots in front of the decimal to keep my magnitude. Okay, so 6,500 milliliters is our final answer. Don't do that. Any questions on that? Any questions on needing to have consistent units? Because that definitely needs to happen. Whenever you're plugging things into an equation, you always want your units to be matching up. All right, so we'll continue on. Here are the other slides. They're much better, much nicer. So you should all have access.
Can I ask a question about rounding up?
Sure. What's up?
So is it always okay to round up? I mean, there's a question on the homework about dosage. Is it okay to round up for sig figs? Is that ever a problem?
To round, you're going to want to be rounding for significant figures.
Yeah.
Yeah, the reason I rounded up to 5
Okay.
was because this is a 7. So if it's 5 or greater, you round it.
Yeah, I understand why we did it.
You want, what was that?
Why we did it. I just wondered if it's problematic.
I'm sorry, I missed something there. What was it?
Sorry, I understand why we did it and like the mechanics of it, but I just wondered if it's problematic to do that.
To round?
And yeah.
Like to get rid of all these decimals?
Yeah, just like if it's a dosage, like the question on the lab.
No, you always want to be honoring correct sig figs. Okay, so
Okay.
if it's a dosage and one of your pieces of starting information only has 2 sig figs, your final answer also has to only have 2 sig figs, because everything else on there is it's not useful information. It's sort of just messy leftover stuff. It doesn't have anything to do with our precision. So yes, make sure that you're rounding.
Okay, thank you.
Yeah.
I have more of a sig fig question, and it is in regards to writing our answers out. Like, would it be appropriate to write 6.5 times 10 to the 3rd power?
If the problem explicitly asks you to write it in scientific notation, then write it in scientific notation. Otherwise, a number like that, I'm fine with you writing out just like that, okay? Because that's not like cumbersome for me to read. Now, if you had a number that was like, instead of it being 2 zeros, it was like 6500000000000. That starts getting really annoying for me to have to count all those zeros up. That I would want you to write in scientific notation. So I would say usually my breaking point is about 3-4 zeros. I would say start switching over to scientific notation. Is that good? Yay?
Yes.
Cool. Okay. Anybody else? All right. So let's go back over to the slides. So we're going to sort of real quickly just thread through the slides just to make sure we didn't miss anything, because these are slightly organized different from what we had going on those really crappy slides. All right, so chemistry, matter, we talked about states of matter, how to organize matter, compounds versus elements, atoms, elements, compounds, we got all this, okay. Representing elements, so we didn't really talk about this. We will expand on this in the next chapter, but just FYI, when we're representing an element, for instance, carbon, we tend to represent it using its symbol that we find on the periodic chart. Aluminum would be Al, lithium would be Li. Some of these things correlate, like helium, He, first 2 letters. Some of them are not quite as direct. Copper is not Co, it's Cu, because its Latin root is cuprum, okay? Lead is Pb from plumbum. If anyone ever does construction or done construction, a plumbum is a string with just a heavy piece of metal or lead at the end of it to get a straight line up and down, all right? We tend to write our elements with symbols. Okay, for compounds, yeah, I guess this wasn't in the last slide, so I do want to go over this. Compounds and composition. So compounds have a definite composition. That's what makes compounds different from, say, a mixture. In a mixture, you can have varying compositions, like salt water, for instance. We can have more salt, less water, less salt, or more water, less salt, whatever. When we're dealing with a compound, it has a specific composition. And there's a law that's called the law of constant composition, or the law of definite proportions, which means that in order for it to be whatever compound you happen to be talking about, it has to follow that recipe. So here we've got hydrogen and oxygen, and we're going to use a little battery, and we're going to, well, this one breaks water apart into hydrogen and oxygen, but you can go the other direction and form a water molecule. Water's formula is H2O. That would be its constant composition. If I want it to be defined as water, if I want this piece of material, matter, to have properties of water, it needs to have 2 hydrogens bonded to 1 oxygen, all right? If I wanted it to be salt water, I have a lot more play in that because it's a mixture. So do know law of constant composition. Mixtures, on the other hand, we can vary their proportions. We have heterogeneous and homogeneous. Heterogeneous, just remember the root hetero being different, homo being the same. So on the left here, this hunk of granite would be a heterogeneous mixture because there's areas where we have more quartz or feldspar and areas where we have more, looks like that's biotite. On the right, we've got a homogeneous mixture of this suspicious blue substance that's been dissolved in water, and now it's evenly mixed throughout. We would also call a homogeneous mixture a solution. Okay, we talked physical properties. Yeah, we're good here. Chemical reactions, we went through all that. Filtration, distillation, chromatography. We didn't have this in the previous slides, so just real quickly, some info on energy. So when we're talking about energy, like we can sort of take the whole universe and divide it into two different sections, one of them being matter, which is the stuff that makes up our universe, and then the other would be energy. That's what allows the matter to do something, right? If we didn't have energy, it would just be a bunch of matter that was really boring and never changed and evolved and changed and broke down and came together. So when we talk about the word energy, we're talking about the capacity to do work, for something to do work or transfer heat. And when I say work, I don't mean like going to a job, but a job is a form of the physics version of work. Work is the energy transferred when a force is exerted on an object, and it allows that object to be displaced, moved, changed. Heat is the energy used to cause the temperature of an object to increase or decrease. So if I'm heating something up, I will increase its temperature by pumping energy into the system. Over here, we can see this is mechanical work, and this would be a heat situation. Force is any push or pull on an object. That's, you know, we get do a little bit more physics when we get into electrons, but not a whole lot of physics. So if you're scared of physics, kind of like I am, we won't be doing too much of that, okay? So with energy, we kind of split energy into two different things. We can have kinetic energy, which is the energy associated with motion. Kinetic is movement. Kinesiology is the study of movement in the body. So if we're trying to calculate kinetic energy equals 1/2 the mass of an object times the volume squared, or rather the velocity squared. So if we have more mass, we have more energy, right? If a 2-year-old runs into you, that is not as devastating as if a 25-year-old runs into you, because a 25-year-old is bigger, unless it's a really big 2-year-old. Velocity is another thing as well. So somebody running up to you and giving you a hug does not have as much kinetic energy as a car driving up to you and giving you a hug at 60 miles an hour. Another type of energy is potential energy. This is energy of an object, and it depends on where its motion or its position is compared to other objects. So if you are sitting underneath a tree, you have very little potential energy. If you use some of your stored energy in your fat cells to climb that tree, so you transfer your stored energy into kinetic energy by climbing that tree, you're now sitting at a higher height off of the surface of the earth. So gravity could potentially pull you back down. That is stored potential energy. Other things that are stored potential energy, springs. So like when you take a spring and you smush it together, there's a certain amount of stored energy in there for it to open back up. Food is a source of potential energy. TNT, unstable compounds are also, they store a lot of potential energy in them, just based off of how their atoms are arranged. All right, so we went over all the SI units. You will know those, and the base units for the metric system, and we talked about prefixes as well. Being comfortable with these, I gave you guys King Henry died drinking chocolate milk, so you're good for kilo to milli. We've got some smaller ones here. Mass The SI unit would be a gram. Length is a meter. Volume, we've talked about that being a derived unit. So a meter times a meter times a meter, or meter cubed. So derived unit meaning it's derived of other units. Density is also a derived unit. Let's move this on. Okay, we did that. We talked about temperature. Here are the two equations for switching out between Fahrenheit and Celsius. Fahrenheit will equal 9/5 times degree C plus 32. And then Celsius will equal 5/9 parentheses Fahrenheit minus 32. Will you need to have conversions memorized for the test outside of King Henry died before drinking chocolate milk? You will want to know, let's go back. I will want you to know micro and no mega and giga too. No micro, mega, and giga. Outside of micro, smaller than that is the pico. You don't need to know that one. What do we have? Nano, pico. So yeah, really micro to giga should be able to get you through. Okay. All right. Energy. So the unit of energy that we use, the SI unit of energy, this wasn't on the previous slides, but the unit we use is a joule, capital J, named after James Joule. A lot of times you'll see it as written as a kilojoule. If we're talking about calories, so, and this is different than your nutritional calorie. So a little c calorie, lowercase little c calorie, is equal to about 4.184 joules. These two numbers will show back up a little bit later on, this 4.184, because that's the heat capacity of water. That's why those two relate to each other in that way. But know that the nutritional calorie is equal to a kilocalorie or 1,000 little c calories. So big C calorie, or the nutritional calorie, is 1,000 of these little guys. So, I mean, while we're here, why don't we just do an example on some of that energy. I think we do end up coming back to it, but you know what? No, we're not going to do the conversion yet. We'll do the conversion a little later. Sorry, we haven't gone over dimensional analysis yet, so I don't want to do it just yet. Sorry, all of my classes, all of my chem classes, no matter what they are, the first like 2 weeks are the same information, but it's like just different enough. So bear with me. We'll start to deviate in a little bit. Okay, so we talked about density, and density also being a derived unit, meaning that it is composed of two other units. Sometimes it's grams per milliliter, sometimes it's grams per centimeter cubed, sometimes it's pounds per yard square, yard cubed, a couple different things. So density is a physical property, which means that an object doesn't have to change what it is in order to express its density. And it has units that are derived from other things. Here are some common densities. So air has a density of 0.001 grams per centimeter cubed. Water, which tends to be our standard for most things, has a density of 1. Table sugar, 1.59 grams per centimeter cubed, meaning it's got more mass packed in the same volume. Gold here, 19.32, so very dense material down here. All right, we talked about scientific, or rather significant figures. So the difference between exact and inexact or measured numbers. Exact numbers are discrete counting objects like 12 eggs, or conversion factors like 1 meter equals 100 centimeters. That's the definition. Inexact or measured values will always have some sort of error to them, so we have to honor significant figures. All right, accuracy versus precision. So just know, be comfortable with these words. Precision is a measure of how closely individual measures agree with one another. Accuracy refers to how closely individual measures agree with or the true value themselves. Okay, so when we're looking at this bullseye here, this has good accuracy and this would be good precision, because all three of them are where they need to be and they're all close together. All right, so you're accurate and precise. This bullseye here would have poor accuracy because you're not hitting your target, but you have really good precision in that all of your darts have clumped together. So you actually have a pretty good shot. You just have to figure out how to kind of drop it down and to the left. This one down here looks like what my target looks like. My husband and I actually, one of our quarantine things has been shooting bows and arrows, and this tends to be what mine is. It's poorly accurate and poor precision. So, you know, we're working with them. All right, so sig figs, we already talked about sig figs. The last part of this chapter is dimensional analysis, and the slide only gives us, or the slides only give us one slide on dimensional analysis, but we're definitely going to spend a little bit more time than one slide on it, because I think in general, Chem 1, Gen Chem 1 is like all dimensional analysis. That's all that we're doing. So what is dimensional analysis? It's just a fancy way to change units. It's a way for us to shift from one unit to another unit. How we do it is we apply conversion factors. An example of a conversion factor would be 1 inch equals 2.54 centimeters. A conversion factor are just equalities. It's two things with two different units, but they're equal to each other. We set up a ratio between those two things. So I can write it as either 1 inch over 2.54 centimeters or 2.54 centimeters over 1 inch. Either one is valid because it's the same thing over the same thing. So, you know, the same thing divided by itself is 1. So this is equal to 1, this is equal to 1. Depending on which direction I'm going in my unit changing, I would use this one or this one. Like if I'm going from centimeters to inches, I'd probably want to use this one. If I'm going from inches to centimeters, I would use this one. And we use these ratios to allow units to change and or cancel. And, this again, this is like literally the only slide on this. So we're going to go back to our board here and I'm going to write a couple things. Okay. So this is our general formula for a dimensional analysis. It's going to be given info times your conversion factor and this will equal your final info. Or another way to write this is given units times, I'm going to put a fraction bar underneath it. I'm going to put given units. Over it, I'm going to put desired units. And this whole thing, if we look here, given units is above the fraction bar here. Given units is below the fraction bar here. So given units will cancel and we're left with just our desired units. So this is sort of the skeletal structure for dimensional analysis. And again, dimensional analysis sounds scarier than it actually is. It's just converting. So Let's do one. I just feel like it's easier when we have an example. So how many, let's make that an M, many feet are in 108 inches? So I'll walk you through this one together, and then we'll do it together, and then I'll have you do the next one. So when looking at this, because we're so comfortable with feet and inches, those things are so like synonymous with us with like everyday life that you probably are just thinking, oh, I'll just take 108 and divide it by 12. But I want you to get in the habit of working it in dimensional analysis. So we always are going to start with, I'm going to write it out too. My given information is 108 inches. What I'm trying to find is feet, and you're always going to see me writing given and find, because this again helps to massage that the critical thinking where you know, it's not just this problem you know how to do, but you'll be able to attack any dimensional analysis problem. So we start with our given units or our given info, which is this 108 inches. I need to multiply it by a conversion factor that somehow relates inches and feet to each other. So again, a conversion factor relates those two things to each other. So I know that 1 foot is equal to 12 inches, right? It's like just the definition of what it is. So we can write that in a couple different ways. We can write it as 1 foot over 12 inches or 12 feet over 1 inch. Now, which one of these are we going to use? That's dependent on what our given information is and what our desired units are. So given units always go on the bottom. Desired units, which are feet, will go on the top. So we would want to use this one for our conversion factor. So over here, I'm going to write it in as 1 foot is equivalent to 12 inches. Now, because these two things are equal to each other, it is a value of 1. So I'm not changing the magnitude of my number. I'm just changing the units. Yes, 12 inches in 1 foot. Blech. Thank you. Yeah, you guys gotta help me out there if I'm, oh no, oh no. Okay, that's all right. So what did we say? We had given 108 inches, find feet. Our conversion factor is 12 inches for every 1 foot, or, thank you, 1 foot for every 12 inches. My bad. All right, so 108 inches. We multiply this thing by the conversion factor. We're going to use this one here because inches will go on the bottom, feet will go on the top. So 1 foot for every 12 inches. What happens to our inches? They disappear on us and we're left with just units of feet. And you may be thinking, well, yeah, duh, that's what I would have done. I was just going to take the number and divide it by 12. Well, they're going to get more complicated with time. So I want you to get comfortable with setting it up in dimensional analysis. So we got 108 divided by 12, and I end up with 9 feet. Now, let's talk about significant figures here. My given information has 3 sig figs, okay? My conversion factor has an infinite number of sig figs. Remember that your conversion factor is not going to be your limiting reactant, or not your limiting reactant, but it's not going to be your limiting sig fig factor, okay? You're going to want to go with the given information. So if this is 3 sig figs, my final answer over here is only showing 1 sig fig. So what I need to do is I need to write this in a way that it has 3 sig figs. How do I write 9 with 3 sig figs? 9.00. Okay, I give it 2 more pieces of significance. So we can do this dimensional analysis in a multi-step as well. Let's do a multi-step together, and then I'll let you go on your own with a problem. All right, so let's say I want to know how many centimeters are in 4.2 feet. So when looking at this problem, just because I've done so many conversion factors, I know that this is probably easiest. It's going to be a 2-stepper because I don't know a direct relationship between feet and centimeters. You may somewhere buried in your brain know the conversion between feet and centimeters. I don't know it. But I do know that I usually have really good access to feet and inches, right? I know their relationship. And then I know very well inches to centimeters. I'm gonna make like a little flow chart here. So when I'm solving this problem, I'm gonna wanna go from feet to inches and then inches to centimeters. So I'm gonna put my given information here is 4.2 feet. I'm trying to find centimeters. I've got a flow chart here, and I do need some conversion factors. So I'm going to fill in my conversion factors. 1 foot is equivalent to 12 inches. And then I know that 1 inch is equivalent to 2.54 centimeters. That was on like the last slide we were looking at. And it'll be on like basic conversion sheets, so you can just trust me with that. So with our skeletal flowchart, we always start with our given information. So I'm going to write out 4.2 feet. I am not even going to worry about centimeters right now. I'm just going to worry about getting from feet into inches. All right, so I know that for every 1 foot, I get 12 inches. Don't get freaked out by these bars that I'm drawing here. This is a divider bar. This is a multiplier bar. So you can just think of that as like a multiplication symbol right there. Okay, so feet cancel. So now I'm at this sort of, I've leapfrogged into inches. So the next thing I want to do is go from inches into centimeters. Some people like to stop and solve. So they'll solve their problem now. I just kind of like to chain them all together. So that's what I'm going to do. So the next thing I'm going to do is convert from inches into centimeters. So if inches are above the fraction bar here, I need to get rid of them by putting inches below the fraction bar here, and my desired unit is centimeters. Then I just fill it in with their relationship. 1 inch equals 2.54 centimeters. What happens to the unit of inches is they should cancel each other out. So I don't think about dimensional analysis as, oh, I've got to multiply when I'm going this way and I've got to divide going this way or vice versa. I just set it up so that my units cancel and let it tell me what to do. So if you're sitting on top, we multiply. If you're sitting on bottom, we divide. So in this case, I would take 4.2, I'm going to multiply it by 12. And then I'm going to multiply it by 2.54. The only thing I have below the fraction bar in this problem are ones, so I don't need to run that through the calculator. Times 2.5. All right, so I got an ending value of 128.016. I can only honor 2 sig figs. Again, don't use conversion factors to limit your sig figs. Use your given information. So if I have 2 sig figs, I get to keep the 1, I get to keep the 2, the 8 tells the 2 to round up. 130 and my units on this are centimeters. So there's 130 centimeters and 4.2 feet. Any questions on that setup before I let you guys do one? All right. So I'm just going to give you one. Oh, I got a question. What would you do if you had numbers other than 1 on the bottom? I'll give you a problem where that happens. Right now, what you're going to do is you're going to divide the numbers. So if they're on the bottom, you divide them. If they're on the top, they're a multiplier. So how many feet are in 3,120 centimeters? So you'll be using similar conversion factors to the last problem. This one is just going in the opposite direction. So set it up using your dimensional analysis. Okay. So this problem, similar conversion factors to the last problem, but we're going in the opposite direction. So my given information here, instead of it being feet, my given information is in centimeters. So I have 3,120 centimeters. I'm trying to find how many feet. So my flow chart is going to look the inverse of the last one. I'm going to start with centimeters. I'm going to go into inches. And then from inches, I will hop into feet. The conversion factors are still the same. So, 2.54 centimeters equal to 1 inch, and 12 inches is equal to 1 foot. So start with my given information, 3,120 centimeters. So sometimes I do the boxes, sometimes I'll do multiply. The conversion, it's the same thing. So I want to go from centimeters to inches, so I'm going to use this thing here. I know that my centimeter part needs to go on the bottom, so it's opposite, and my inch needs to go on the top. From there, I fill in the values, 1 and 2.54. And then I'm going to stick the next one on. So inches will go on the bottom so that it can cancel. Feet will go on the top. 1 foot is equal to 12 inches. This cancels, centimeters cancels, and centimeters cancels. Always checking to make sure your units cancel so that you know you've set it up correctly. 3,120 divided by 2.54 divided by 12. So for this problem, I got 102 feet. 3 sig figs here, because I don't know if that 0 is significant. So I'll just honor 3 sig figs here. Any questions on that problem? Any questions on dimensional analysis setup? All right. Let's pull up a couple more, because you can never have too much dimensional analysis. Really, just can't. All right, so in one of the guided notes, we've got some of these examples. Let's look through here. Oh, you know what? There's actually, let's pause on this. One more thing I want to show you with this is just let's say that we are given that we have 1,500 kilograms, and I want you to find grams, okay? So you can solve this however you want. You can solve it in dimensional analysis, or you can solve it hopping if you prefer to do that. I'll do both of them at the end. Okay. So not a super complicated conversion. And two ways you can go about it. So one way is to set it up in dimensional analysis. I start off with my given information, sorry, kilograms, and I want to go to grams. So I'm going to put kilograms at the bottom and gram at the top. I know that 1 kilogram has 1,000 grams in it. Why do I know that? Because I just know a lot of these. You will get familiar with them the more you use these. What happens to grams, or rather what happens to kilograms, is that cancels, and we plug this into our calculator. We end up getting 1, 2, 3, the 1,500,000. If you're like, whoa, 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 but I remember King Henry. Okay, yeah, King Henry died before drinking chocolate milk. Those are our prefixes. If we're starting at kilo here and we're going to gram, which is an example of a base unit, we hop our decimal 1, 2, 3 hops. So my 1,500, decimal here, 1, 2, 3, fill in the zeros, we get the same number. Okay, so if you prefer 1, do 1 within the metrics. If you prefer 2, do 2. Okay, hop around, that's fine. Get comfortable with it. It'll start to hopefully be real easy for you to convert between, you know, milligrams and kilograms and things like that. Questions on either of those two options? Now, can you hop like this in the British system? No, we can't. That's why the British system sucks. Because 12 inches in a foot, 5,280 feet in a mile, it just doesn't work. So you don't have that base 10. All right, let's go back over here. I want to do, okay, do this one here. So he says, if a woman has a mass of 115 pounds, what is her mass in grams? And look at it, it even gives you the conversion factor. And then after you've done that one, why not set up number 3 as well? How many minutes are in 1.4 days? And that's also in dimensional analysis. So I want you to do both of those in dimensional analysis. Which one are we doing? Okay, so when looking at the screen, David, do 2 and 3. So do the woman's mass, changing from pounds to grams, and then do minutes to days. Cool. About a minute here to finish up. Okay, so let's look at this first one. So if a woman has a mass of 115 pounds, what is her mass in grams? So we know our given information is 115 pounds. Our find is grams. So there's my conversion factor for me. So we start off with our given information. We use our conversion factor in such a way that units are opposite of each other. So pound goes on the bottom, gram goes on the top, 454 for every 1 pound. Pounds will cancel and we'll be left with units of just grams. And then I got 52,210. We're going to go with 3 sig figs because the beginning one has, our given one has 3 sig figs. So 5, 2, 2, 0, 0. Okay. So with conversion factors, it's always the same setup. Just get the units on the opposite side. Let's look at this one down here. So how many minutes are in 1.4 days? All right, so given unit is 1.4 days. We're trying to find minutes. So if I was to make a little flow chart, I would say I'm going to go from days into hours and then hours into minutes. All right. And then when writing it out with the actual numbers, I know that 1.4 days is where I'm starting. First thing is to get into hours. So days on the bottom, hour on the top. I know that 1 day has 24 hours in it, but I don't want to stop there. I want to go all the way to minutes. So I'm going to put the hour on the bottom and the minute on the top. 1 hour will give us 60 minutes. 1.4 times 60. So quite a few. 2,000. 2,000. Yeah, 2,000 minutes. The number that I got in my calculator was 2016. We get to do 2 sig figs, so we keep the 2 and the 0, cut everything else off and fill it in with zeros. So that's where I got the 2,000. Any questions on dimensional analysis setup? All right. Yeah, let's look at some squared things. All right, so some helpful things to note. 1 centimeter cubed is equivalent to 1 milliliter. I think we already talked about that. 1 meter cubed is equal to 1,000 liters. So. Here are some volume. I'm trying to think which one I want.
I have a question in regards to conversion tables maybe in our textbook, I'm not able to find any sort of like reference tables in the textbook.
A conversion table. There's, let me see here. Should be one. Usually there's one sitting in the lab manual. I'd like to stick them towards the front. All right. In that first lab, there is some conversion tables on there. Let me look on Moodle real quick right here and see if we've got one. If not, I will get a conversion sheet together for you guys so that you can just easily reference it. Because yeah, it's nice to have that stuff sort of in one spot. Instructor information, 151 equations. Please log in, log in. So this is got some of the equations. This doesn't have the conversion factors though. Let me go ahead and inside back cover, it looks like there's one. And then let me go ahead and chat with some of the other chem instructors who've already done 151 just to make sure that I'm consistent with them on what formula sheet they specifically want me to use. I'll get back to you guys on that by Wednesday, okay? Cool. I don't know. Do I want to do one of these? I think we're going to stop for today with that. Yeah, we'll stop there. So we're in a good spot anyway. We're pretty far ahead. So if you have questions, you know what? Before anyone goes, I'm gonna move us. Let me stop sharing. Okay, I'm gonna move us into, or move you all into some breakout rooms. I don't know if you guys have done breakout rooms yet in any of your other classes. It's just gonna take you and put you with like 4 other students. So you can talk with each other for just a couple minutes at the end here. Maybe say what your major is, because your major might be the same as somebody else. And then give each other your email information so that you guys, if you're struggling during a lab, can get into contact with another student. So you're not always necessarily having to reach out to me. Not that I don't love you guys reaching out to me, but just so that you guys can have assistance from a different angle, okay? So if your camera is not on currently, go put some clothes on, get out of bed, and say hello to a couple of your fellow students, all right? So I'm gonna go ahead and pop this in right now. So there's 23 of you. All right, we'll do 5 rooms. Okay, so it's gonna prompt you to join a class or join a breakout room. So you'll just click on that and then meet up.
Cool.
Hey, I'm just hopping in for a second just to say hi, let you guys know that once you've gotten each other's information, you're free to go for the day. Unless you have a specific question for me, then you can stay around, okay? Otherwise, I'll see you all on Thursday. All right, bye.
Bye.
Yeah.
Mine is kind of long. Hold on.
Hey there, I'm sneaking in just for a second, just to say hey and let you guys know that once you've exchanged each other's info, you can sign off for today. Unless you have a specific question for me, then feel free to hang around and I'll chat with you, okay? Otherwise, I'll talk to y'all on Thursday. All right, bye.
Okay. Bye.
Hey there, I'm just sneaking in for a second just to say hey and let y'all know, once you've gotten each other's information, you're free to sign off for the day. Unless you got a specific question, then you can hang around. Otherwise, I'll see y'all on Thursday, okay?
Bye.
Hey, just sneaking in for a second just to say hey and let y'all know that when you've gotten each other's information, you're free to head out for the day. Unless you have a specific question, then you can hang around, okay? Otherwise, I'll see y'all on Thursday.
Thank you.
All right, bye. That's the bachelor's. Hey, just sneaking in real quick. Just 1 second. I wanted to let you guys know that once you've gotten each other's info, you can chat for a little bit, but then you're free to go for the day. Unless you want to hang around and ask me a question, I'll be hanging out in the main room, okay? Otherwise, have a couple days. What was that?
Will you be here till 4 like last time?
Yeah, I'll be floating around. I'm just a couple minutes from my computer. So if you just shoot me an email, we can meet up and talk about lab stuff, okay?
Okay.
Okay, cool. Bye.
Thanks.
Mhm.